the potential uses?
Well, as I was saying a moment ago, go-bodies are actually, when I started looking really hard, I found that go-bodies exist in nature. And I mentioned the example of hirudin and bivalirudin. What distinguishes our technology is the means of combining two binding sites, two binding things. What the chemists who've worked on this kind of thing before have always wanted to do is to join these things together so they can react with two different objects. And they've usually made the link very rigid. And I could show you a little drawing to show the kind of thing that has been very carefully developed. But this is completely prevented from the two binding things reaching the same target. It's meant to connect together two different targets, and the link between the two binding things is rigid. And that's called a diabody. Now, what I thought of at the very beginning was, if we're going to have the two things binding us to the same target, they have to be able to bend round and adjust their position so that both can come into focus at the same time. Now that then led me to think of a flexible link, and then to ways of making that from nucleic acid. Now what we do then is simply to attach a nucleic acid tail to each of our binding things, and then let them match together. We design the nucleic acid sequences so they are complementary, they bind to each other, and then the thing forms spontaneously, as is shown in this drawing, to form a co-body with a flexible linker. And what's more, you're not limited to two. There's no reason why you shouldn't have three or more. And the next little picture shows three such new binding things all joined together in one co-body, and on top of that, at the back of it, is a functional unit. That might be, as I've drawn it with a radioactive warning sign, that might be a radioactive thing to go and kill a cancer cell or a bacterium, or it might be some other toxin for the same kind of person, or just a signal, something that shines a light so you can see it under the microscope. So you've got this enormous potential. And all you need to do is to have your binding units or your functional units, each with attached to it a single strand of DNA. And that's the first difficult chemical part of the thing was, how then are you going to attach your DNA to protein? And that took some doing. We're talking a few years ago.
Right.
That took some doing. But there are many ways of doing it now. It's well known. What people are not doing is combining the two things together. So the methodology is based upon this idea. Two or more binding things, flexible joints, therefore nucleic acid, and then you get all sorts of other benefits from the use of nucleic acids. Because you make the thing, you just mix them together, and they're made.
Right.
It's done. It's a few seconds, a few milliseconds, you might say. And then if you want to make a new one, you just modify one binding thing. You don't have to go through a whole genetic engineering business taking weeks or months or years. Just make one new binding thing, stick your nucleic acid again, make a different mixture, bingo, it's done. And it happens. You can see it happening.